Hello, my name is Kim. I came from IBM Anomaly Research. As you can see from my title, this paper is about page change memory and also about enterprise storage system. And by the way, I put this, I took this photograph from my office, and I put this photo here to let you know how nice working at IBM Anomaly. So let me give you a very brief background of this study. In 2012, Micron built a prototype SSD with their latest PCM devices based on 45 nanometer technology. And they provided the SSD to IBM, thankfully. And we were curious about these performance characteristics of this SSD. So our team was asked to do some measurement study because it was our specialty. We did many times for other SSDs. So we could get some numbers, and it was very different from eMMC-based flash SSD. And then we were curious, what does that mean? Whether it can make enterprise storage system better or not. So we did run simulations, storage simulation for two typical storage use cases, storage tiering and storage caching. So I have two parts today in my presentation. The first part is about performance of page change memory, and the second part is about the simulation result. Okay, performance. This is also Almaden. So I may want to explain a little bit about basic technology differences between flash memory and page change memory. As we all know that flash memory remembers data bit by capturing electric charges in its floating gate. Page change memory is different. They don't rely on the existence of electric charge. Instead, they use the material pace to remember data bit. There are two pace in PCM, amorphous pace and crystalline pace. And to change the pace, we have to melt the material. And we control the melting temperature and the duration, and we can form amorphous pace and crystalline pace. Because this pace change memory doesn't rely on the electric charge, it is known that people saying that PCM is more scalable, can be smaller in. Okay. So let's talk about PCM write latency. As I mentioned before, there are two write operations, reset operation and set operation. And as you can see here, set operation takes longer time. And if you have ever been interested in page change memory before, you must be familiar with this number, 150 nanosecond. This is frequently used, have been used as PCM write latency time because we need at least this amount of time to write in PCM. And if we compare this number with the other technologies like flash memory and DRAM, we know that on flash memory, page program time takes at least 200 microseconds. And DRAM, as you can see here, if we use that number, you can see that PCM is more than 1,000 times faster than flash and only 3 times slower than DRAM. But how about write throughput? So as I mentioned before, we have to melt the material. And we need power to do that. If you think about the chip, maybe we want to melt multiple bits, not only one bit, and we need more power. So interestingly, the PCM technology, the write throughput is limited by the budget of power, the chip-wise. So it's a very interesting example. This paper was published in 2004 by ST Microelectronics people. And I came to this paper when I tried to identify the source of the number, 150 nanosecond. And I copied several sentences from the paper. And actually, I could find the number, 150 nanosecond. A reset pulse of 40 nanosecond, a set pulse of set of 150 nanosecond. Interestingly, the very next sentence was talking about only 4 bits can be written at this specific chip during that time. So it resulted in very limited write throughput of 2.5 megabyte per second. And actually, the right number for set time was 200 nanoseconds because there was additional 50 nanosecond of circuit delay. If I compare the write latency with flash memory, we just see that PCM set operation time is 200 nanosecond, and page program time we can assume 200 microsecond. We can see that PCM is 1,000 times faster in terms of write latency if we write only 4 bits at the same time. If we compare write throughput, 2.5 megabyte for PCM versus if we assume 4 kilobyte of page size, then it is calculated to 20.5 megabyte per second. So flash is 10 times faster. Issue is we researchers are not very careful about using the numbers. This is one of the examples. And I copied the table, this table from a survey paper about PCM technology published last year. And it is saying that PCM 100 megabyte per second versus 2.5 megabyte per second for NAND flash memory. So I want to make some clarification today. So write latency is different from write throughput. We all know that, storage people. And 150 nanosecond, 200 nanosecond, or whatever, 100 nanosecond for PCM, this is about material level performance, not chip level performance. It is, more limited by the power budget. So, and chip level performance does not, it can be different from the SSD level performance. Okay? So now let's talk about the SSD level performance we measured from the latest prototype SSD from Micron. So this SSD using 45 nanometer technology and having a 64 gigabyte capacity, and we compared this SSD to one of the greatest eMMC flash SSD, which is having 1.8 terabyte capacity. So let me explain a little bit about our measurement framework. We used Red Hat Linux, and there's a device driver, Linux storage software stack, and we have to modify the device driver as well as the Linux kernel to capture fine-grained I/O latencies for every I/O in nanosecond level. And we had a workload generator, and we retrieved the latencies while running this workload. So let's talk about the real numbers we measured. So 4K random read latency for 5 million samples. There are two graphs. So red is for PCM SSD, blue is for flash SSD. And this graph, x-axis is 0 to 200 microsecond time, and y-axis is percentage. So this graph is showing the distribution of I/O latencies. And as you can see here, PCM SSD 4K random read latency average value was 6.7 microsecond, which is 16 times shorter than eMMC's 108 microsecond. Another point is maximum and standard deviation. The maximum was PCM case, it was less than 200 microsecond for 5 million samples, while the flash case, it's over 54.7 millisecond. So huge difference. By the way, the USENIX, which is the first PCM SSD prototype built by UCSD researchers, they reported 38 microsecond for 4K random read latency. 4K random write for 1 million samples, the same way, 0 to 400 microsecond for x-axis. For PCM case, the average latency was 128.3 microsecond, and the flash case, 37.1 microsecond. Actually, this number is from write buffer, RAM buffer. The SSD we used was, it has 1.8 terabyte capacity, and they have huge amount of write buffer, and they protect the write buffer with big capacitors. So they use aggressively the write buffer. So this number came from there. So it's kind of unfair. Somehow the PCM SSD designers, they decide to not use the write buffer to expose the real PCM performance. This is prototype. Okay. And so UNIX case, again, 178 microsecond used to be. No, not used to be, it was. Okay, summary. So for read, PCM SSD is 16 times faster, and for write, 3.4 times slower than flash with DRAM. Okay, our next question was, what does that mean? Is it really useful for enterprise storage system or not? So we did simulations. So first simulation was multi-tiered storage simulation. The idea of the tiered storage system is we want to identify hot data versus cold data, and maybe we want to put hot data to the flash, faster flash, and cold data to cheaper disk drive. By doing this, we want to maximize performance while minimizing the cost. That's the idea. If we include PCM in this equation, maybe we want to identify hot read-intensive data and hot write-intensive data because PCM was slower than flash for the write. By the way, this tiering simulation, we need to have assumption for price. If we don't care about price, then there's no point. There's no point. I mean, you can just put everything to the flash or PCM. So to have assumption about the prices, we studied the market for disk drive and eMLC from Dell's website last year, June. And the difficulty was for PCM because this SSD is not available commercially. So our best effort was asking opinion to experts, and they gave us 4 times more expensive it will be than flash. That's assumption, but we believe is reasonable enough. So normalized cost for PCM 24, flash 6, and disk drive 1. We use this assumption for our simulation. So let me explain a little bit more about our storage simulation method. We assume a hypothetical storage device having X% of PCM, Y% of flash, and Z% of disk drive, and we estimate performance in terms of IOPS. I have another slide about this part. And we also estimate the storage cost, so normalized storage cost, not real cost. And our final metric is estimate performance divided by estimate cost. So higher is better. About the tiering simulation method, how did we estimate the performance? We tried 2 different approaches. The first one is static optimal data placement. So actually, this is a simulation based on traces. So we already have the traces, and we have complete knowledge about the traces. So we can know, I mean, in our head, which part should go where. So static optimal data placement means we calculate the I/O traffic, and we place data at the beginning, and there is no data movement. That's a static data placement. But that's not real. I mean, in real world, we don't know in our head. The real world tiering system, normally we do dynamic data movement and reactive dynamic data movement. So we implement very, very simple algorithm for doing that. So dynamic tiering is more realistic, and static optimal is more optimal. So trace. So we ARMA then have everything about storage. Of course, this trace is very important. This trace is from real retail store company, their production system. So 2012 June, 1 week duration. And this graph is showing, the histogram graph is showing the amount of read and write. You can see this is highly read intensive. That the line graph is showing the cumulative amount of data traffic. You can read this graph in this way. About 20% of storage portion is receiving over 80% of traffic. So highly skewed. Okay. This is the result. We tried every possible combinations for PCM, flash, and disk drive. And x-axis is representing PCM, flash, and here our evaluation metric, IOPS per dollar. So here, the best number, highest number, was achieved by 22% of PCM and 78% of flash for dynamic tiering method. Here is better, easier graph to compare. So homogeneous configurations, all disk drive, all flash, all PCM. From here, flash achieves the highest number. If we apply static optimal data placement, we can achieve 3,220 with these combinations. If we apply dynamic tiering, we can achieve this number with this combination. And this is 61% higher number than all flash configuration, which was the best number without PCM. So we have more result in our paper, and these bank traces, telecommunication company traces, all real from all their customers, 1 year duration. The idea is PCM can improve tier storage performance. Okay, let's move to next part, caching part. Storage caching, flash caching, this becomes popular these days. Many companies have product, IBM eGTR server, EMC Extreme Cache, NetApp, Flash XL, Fusion IO, IO Turbine. So the idea is we want to hot data to local flash SSD to eliminate network overhead. So the idea is, what if we use this PCM SSD instead of this flash SSD, or together with this flash SSD? So we need traces again, but I mentioned 3 traces before for our tier storage system, but that was long-term summarized trace for extent level. To simulate cache, we need IO by IO traces. Again, we have everything about storage system, Armada. So we pick 3 traces, 24 hours IO by IO traces from real customers' production system. And we implement very simple algorithm, write-through policy, error replacement, which are the typical choices for enterprise flash cache solutions. And we use average read latency as our evaluation metric because there's no way to improve write performance if we assume write-through policy. So these are our parameters. And by the way, we still want to include the cost assumption into our simulation. So the idea is, if we use flash as our cache, maybe we can just pick some arbitrary number, 64 gigabyte. If we want to PCM instead of flash, maybe we should reduce the amount of capacity because we assume PCM is 4 times more expensive. Or we can reduce the amount of PCM and we can add more flash. Or we can do that one more time. So I can continue to do this, but I pick only 4 configurations. So first 2 is 1 level cache, and the second 2 is 2 level. We put PCM in ahead of flash, and we simulate the result. And by the way, I pick 3 capacities for flash, initial size, 64 gigabyte to 256 gigabyte. Again, the trace distribution, read intensive and highly skewed. So here is the result, and this result is y-axis, the average read latency time, so smaller is better. So first set of configuration, unfortunately, not unfortunately, the flash is the best. I mean, all flash is the best among the other PCM configuration. So we double the capacity. Now the gap reduced, but still the all flash is the best. We double again. Then now PCM improves, can yield a better number than all flash configuration. So basically, I'm not saying the PCM is always better than flash, so we can find somehow to use PCM better than existing system. So we have more result in our papers, media company and medical company, all real customers, traces. Summary and conclusion. Yes, this is also Almaden. So the first point is I want to say this. Let's be careful to pick number for PCM performance. And we are sharing the number we measure in, PCM SSD level. And our simulation result is showing that PCM has promises for enterprise storage systems. And my last concluding question is, PCM phase change memory for enterprise storage, is this silver bullet or snake oil? I hope to answer this by myself, but I can't. So I want to discuss this with you in my post session. Thank you.
Hey, so Mesh from Nimble Storage. Thanks for explaining PCM and presenting your work. It's among the first, at least in this audience. So, but I was hoping that PCM would help solve the problem Flash has with wear out. That when you keep writing to it, Flash wears out, and I believe PCM does not. But you're, based on performance, proposing that Flash be used for write hard data and PCM for read hard data, right? So that's based on IOPS, but based on endurance, I could imagine taking a different approach. So I was wondering what you think about it.
Yes, I totally agree with that point. Actually, the Flash has an endurance problem, not problem, issue, EMLC, TLC, and PCM is known as much more endurable than that. So that's the good point, but we didn't test that because we are more interested in the performance-wise for now, but I totally agree with your opinion.
Okay, all right.
Maybe we should use PCM as to receive the right traffic to make lifetime longer.
Okay, thank you.
Thanks. Dejan Vucinic from AGST. Thanks, Eugene. That was a very nice comparison. I was just a little worried that you were short-selling the right performance of PCM by omitting to mention the capacities of the devices. So while it's true that your device had a lower write throughput and a higher write latency than the Flash device, it also had a much lower capacity. So if you compare it per gigabyte of capacity, then PCM would win over Flash dramatically. So can you comment on that?
Sorry, are you asking?
Well, so you were using 1 gigabit dies on PCM and probably 128 gigabit dies on Flash, or 256 gigabit dies on Flash. So per gigabyte of capacity or storage device, PCM write throughput is actually quite a lot higher than Flash.
Okay, so right. So you are pointing the right performance issue. So because I used the slow, I assume that PCM is slower than Flash.
Correct. I mean, it is slower for the particular pair of devices that you're using, but you're also not comparing apples to apples because of the capacity difference.
Right. That's the right point. So because we are comparing 64 gigabyte PCM SSD versus 1.8 terabyte Flash SSD. So for this specific SSD, I agree with you. And it's actually a difficult question. Actually, in my simulation, I'm ignoring that kind of factors for simplification purpose. But yeah, I understand. So the capacity is a kind of problem still, as I know. PCM. So as you pointed, the performance per capacity, PCM can be better, but at the same time, Flash, it's difficult to, it's not very clear to me. Yeah, it's difficult to answer. Thank you.
He asked half my question. This is David Rosenthal from Stanford. So the other difference between the Flash and PCM was that in your case, Flash was using DRAM write buffers. As I understand it, there's no fundamental reason why PCM can't use DRAM write buffers, right? And if you're saturating the writes, the buffers don't actually make any difference to the throughput, but you're saturating the writes, as he points out, over the devices. And for equivalent capacity, you would be spreading the writes over many more devices. So, and if Flash was writing, and if PCM was writing faster, your results would look very different, right?
Right. So basically, so my assumption for the right part is actually not fair because this PCM flash SSD has a write buffer and this PCM SSD doesn't have write buffer. I agree that. But actually, the reason I did that, I mean, pick the number used that way is, the first one is I want to use as it is, I mean, what I measure. Even though it can be improved in the future, but I want to still use the real number. That's the first reason. And second reason in my mind was actually PCM has some issue for write throughput part. So eventually, as I know, this SSD has to drive a lot of chip at the same time. So somehow, compared to flash, the write has a still issue in my mind. So that was the next part. Actually, this is still simulation. I admit that. So this is the early study, and this prototype SSD is not mature, and yeah.
Okay, Bill Belaski from MSR. So when you did your dollar per IOPS simulations, did you have a bunch of cache in front of it that was cache hitting or something? Because you had a number of 200 IOPS per dollar for a hard disk, and as far as I can tell, that number for the raw hard disk for random IO, that's closer to 1, not 200. So I want to know where that number came from.
Yes, so the dollar is not the real dollar, first of all. So normalized cost. And so simply because I assume 5 milliseconds is a hard disk latency, if I reverse, it results in 200.
Yeah, you get about 200 IOPS, but it costs more than $1 for a hard drive, right?
So normalized
so it's
cost.
normal. So it's not really dollars. It's just okay. So the scale should. All right. Now I understand.
Okay, great. Let's thank the speaker again.